Hey everyone, welcome to Mr. Winter's Chemistry videos. I'm Mr. Winter. Today we're going to be talking about mass spectroscopy, and it's kind of relating more to what we talked about in our last video on isotopes. So if you are feeling a little confused about isotopes or still need like a little refresher, I would suggest watching that video before jumping into what we're going to talk about today. So today we're going to go ahead and jump in and look at mass spectroscopy one more time. Today you're going to need a periodic table, your calculator definitely, pen, pencil, some notes. Don't forget I've linked the graphic organizer to our lesson down below today. So let's go ahead and get into it. We're going to look at, once again, mass spectroscopy. And before we do that, I really just want to define why we need to do mass spectroscopy. What is important about mass spectroscopy in the real world of chemistry? And it's all related to this, the average atomic mass. So the average atomic mass is going to be the weighted average of the naturally occurring isotopes. So remember, isotopes are atoms of the same element with different numbers of neutrons. So if we have atoms with different numbers of neutrons, for example, chlorine 35 and chlorine 37, these different isotopes will have different masses because they are made up of different numbers of things. So the average atomic mass, can be found by looking at the bottom of the elements box on the periodic table. It's right here. It's for chlorine 35.45 AMU. And we talked about that number before. That's the molar mass. It is quantitatively equal to the molar mass. So basically, this is how we determine what the molar mass is. And the average atomic mass has an unofficial formula that I'm going to go ahead and give you. So AAM, average atomic mass, is equal to the mass of the first isotope, mass of isotope 1, times by its abundance, plus the mass of the second isotope, times its abundance, plus the mass of the third isotope times its abundance, plus the fourth, fifth, for however many naturally and stable, naturally occurring isotopes that exist for that substance, you are going to add all those up. So for chlorine, there's only two naturally occurring isotopes, chlorine 35 and chlorine 37. So what we're going to do is we're going to use this mass spec data here, to determine if we can figure out chlorine's average atomic mass. So we're going to go ahead and do that here. Average atomic mass is equal to the mass of the first isotope. We'll take this out to 2 decimal places, so 34.97 times 34.97, make that a little bit clearer, times the abundance. And notice I'm changing it to the decimal form, so 7576, plus the mass of the second isotope, which is 36.97, times the percentage. Remember, we're changing this to decimal form, so 0.2424. And if you plug it into your calculator, once again, I always recommend that you follow along with me. You will actually end up finding that the average atomic mass is equal to 35.45 AMU. So this is a weighted average, so our number should be in between the smallest mass value and the largest mass value, and it is. And I also want to point out, since 75% of our chlorine atoms are chlorine 35, it should be closer to the mass of that first one, and it is. So that's our game of, does this make sense? Does that answer make sense? And last but not least, if you were trying to determine the average atomic mass for an element that exists on the periodic table, you can quite literally check and see, does that equal the number provided to you on the periodic table? So moving on, what is mass spectroscopy? What does this actually do for us? And that's what we're going to go ahead and check out right now. So mass spectroscopy does this. it provides us these quite lovely graphs here. Mass spectroscopy basically determines, so mass spec determines the abundance of the naturally occurring isotopes, determines abundance of the isotopes. That's not how you spell abundance. Abundance of the isotopes. So it looks like if I put a sample of copper into a mass spec, I get this graph here, and there are two naturally occurring isotopes for copper, copper 63 and copper 65. Copper 63 is about 68 or 69%. Copper seems to be 31, 32%. Copper 65, 31, 32%. So we can go ahead and do a very brief approximation of the average atomic mass using our mass number, so 63 times, once again, we'll say that is at 69%, so we'll do 0.69 plus 65, so that's the mass number for this, times about 0.31, since we need to make sure our abundances add up to 100%. We'll go ahead and plug this into the calculator here, and we'll find it's pretty close. It's not going to be exact. Plus 65 times 0.31. The average atomic mass using just a visualized data gets us the average atomic mass of copper to be 63.6 AMU, 63.6 AMU. And that's actually pretty dang close to what copper's average atomic mass is. Copper's average atomic mass is 63.55. But of course, you're not going to be always given this graphical data. You will be oftentimes given the actual specific values. And so these are the actual specific values. And you can go ahead and check your work to see if you get the average atomic mass of copper to be 63.55 AMU. That's what we're going to be looking for using these data. Awesome, y'all. So that is mass spectroscopy. Once again, hopefully you followed along using our graphic organizer. And if you have any questions, feel free to contact me. Have a good day.